All right, welcome to the PowerPoint for Chapter 18. I am going to go ahead and share that, and we will take a look at that. Let us start this from the beginning. And this is kind of a longer one. It is an 85 slide one, but I'm going to kind of skip over a couple of them fairly quickly. So kind of pay attention. If you want to spend more time on some of the slides, the slideshow will be available on Canvas, but you can also just pause the video. Okay, here is the chapter outline, and we're going to focus on different aspects of reactions. We're going to look at kinetics, in other words, how fast a reaction occurs. We covered that in chapter 14, so we have a pretty good idea of that. But the other thing is whether a reaction is possible or not. Can a reaction occur? Okay. One of the big things we're going to look at is whether a reaction is spontaneous. Now, your book definition is a tendency to occur without being driven by an external influence. I prefer the definition, a change that occurs without added energy. Okay, it doesn't have to be fast. Spontaneous is a term for a naturally occurring change. Spontaneous tends to occur without external influence. If you put a hand on a cup of coffee, the heat is going to go from the coffee to your hand, and that's going to occur spontaneously. As you can see here, my coffee cup is giving heat to my hand right now. Okay. All right. I couldn't get through a whole video without you seeing me drink it out of my coffee cup. Okay. Non-spontaneous occurs only if driven. We have to add something to it. For example, if I want to heat up the coffee pot, I can put it on a stove or heat it up in some other way. Okay. Spontaneous processes, solvation of a soluble salt. If we dissolve something, ammonium nitrate is quite interesting because when it dissolves in water, ammonium chloride does this as well, it gets colder. Okay. Expansion of a gas and diffusion. Gases tend to mix, certain phase changes, ice melts at certain temperatures, water evaporates, some reactions. If I put sodium on water, it's going to react like crazy. Iron rust. Now notice the kinetics of these two reactions are vastly different. Iron rusting is going to be a lot slower. Sodium reacting with water is going to be almost instantaneous. So when we're talking about spontaneous, the speed of the reaction has nothing to do with it. Here's another one. We can take a heated metal cylinder into water, and it is going to raise the temperature of the water. Okay. A lot of spontaneous processes are exothermic. So if I take a gas and I expand it, it's going to actually expand into this. It's going to expand irreversibly. We don't really have a change in enthalpy, although there are some gases that are going to cool down in this. That's the nature of air conditioning, but we'll cover that at a different time. Okay. When we look at thermodynamics is a big fancy name that means heat changes. If we take a look at the first law of thermodynamics, which we covered in Gen Chem 1, the first law is energy cannot be created or destroyed. We can change it from one form to another. We can even change it to mass or mass to energy. We'll cover that in chapter 25. We want to look at a state function. A state function is not like levying taxes or passing bills. It depends only on the initial and final state. We'll look at the delta U equals Q plus W, but I'm not going to focus on that very much. I do want you to remember that an exothermic process has a delta H that's negative. An endothermic process has a delta H that's positive. Okay, so enthalpy alone doesn't predict spontaneity. Remember the ammonium nitrate dissolving in water and getting colder. So that is one where the enthalpy is positive, but it still occurs spontaneously. Okay, so there's another factor that depends on this. There's a couple others that are listed here. So enthalpy, and then the other factor is entropy, which we call delta S. Delta S is change of entropy. S is the measure of the absolute entropy. We'll talk about that here in a minute. Okay, energy and matter tend to become disordered. I don't necessarily like the term disorder. I like focusing on the number of possible arrangements or the possible states that something could be in, but lots of textbooks like to use the disordered, so I will at least go through that. Okay, so entropy is a level of the disorder of the system. Okay, I'll accept that for the moment. Its symbol is S. It's actually a measure of the total possible arrangements. The more arrangements, the more disorder that you have. Okay, disorder is more probable and it has a high entropy. Order is less probable. So for example, if I drop a deck of cards on the ground, it's probably not going to be more organized than when I dropped it. Okay, so entropy is basically the dispersal of energy. The system moves to a higher state of disorder, or in other words, to the state where it has more possible arrangements. The thermodynamic property is called entropy, or S. Now we have a second law of thermodynamics. I can't talk. Remember, the first law of thermodynamics is you can't change energy from one form to another. The second law says that a spontaneous process results in an increase in the entropy of the universe. Now we'll talk a little bit about that. That's going to be important for us to understand. So basically, in the first law of thermodynamics, you can't come out ahead. You can't come out with more energy than you started with. In the second law, it's not only can you not come out with more energy than you start with, some of it's converted to entropy, so you're going to end up losing energy no matter what system you have. Okay, so there's a lot of forms and definitions for the second law of thermodynamics. I've kind of stated one. Okay, let's take a look at S. S measures disorder. No, it really measures the more possible arrangements, but I'll accept the book's value on this. Entropy for a solid is going to be the lowest because it has the fewest ways it can be arranged. A liquid has more arrangements. A gas has far, far more. Okay. Aqueous is usually between a liquid and a gas, but it depends on the system. We talk about a state function. State functions are where we have delta S equals the final minus initial. And the reaction for delta S is the entropy of the products minus entropy of the reactants. Now notice we have this little zero here. This means that there is a table that has the standard entropy with all the different things that we can look at in the back of the book. This is the equation that we'll use most of the time when we're finding delta S for the reaction. Okay, nothing has an S of 0. Well, actually, S equals 0 at 0 Kelvin for a perfect crystal. That's actually the third law of thermodynamics. Okay, and as temperature increases, the entropy is going to increase. Now I know in the lab we are assuming that delta S is going to be constant. Remember, that is delta S for a reaction and not S. And it does change a little bit, but it's not significant change in the lab we're doing this week. Okay. As the size of the container increases, the number of ways that we can arrange something increases. So therefore, we have an increase in entropy of the system. Liquid water is greater than that of solid because it has more arrangements. In the solid, they're very arranged, very organized. Energy is more dispersed in the liquid because in addition to having things at one very simple thing, we can have things move from here to here to here. Whereas in a solid, there's 1, 2, 3. They can only be in one particular way. All right. If we take a look at entropy in states of matter, you can see this a little bit more. Okay. Bromine liquid versus bromine gas. Notice the arrangements there. There's a far more arrangements in the gaseous state, so it's going to be a lot greater than that. All right, so we can predict entropy. If we take a new deck of cards, you know, when you open a new deck of cards, all the cards are in order. And if we shuffle them, there's going to be a lot more possible arrangements. Water and ice are another example. So in this one, a new deck of cards is going to have a higher entropy. In this one, water is going to have a higher entropy. So if we take a look at the ice, see the definite arrangement. In the water, there's a lot of different possible arrangements there. Okay, now one of the calculations we can do is Q reversible over T. Now I really don't like using Q reversible because it's not really something that we're ever going to be able to attain, but theoretically we're going to talk about it a little bit. So the change in entropy is given by Q reversible over T, where Q reversible is a heat gained or lost by the system during the process, and T is the absolute temperature. Now, a reversible is one that can be returned to its original state. An irreversible process cannot. So if I break a coffee mug, I can't really put it back together. I mean, I could remake it, but I would have lots of great increase of entropy in order to do that. One thing I want you to notice is that all real processes, they're not really reversible. So this Q reversible is more of a theoretical ideal. We can approach the ideal and get some measurements out of it. So again, this isn't real. We could take the heat away just as we add the energy. Easier said than done. In everything that we do, we're going to have an increase in entropy of the universe, so it's not really reversible. A better definition is that came up with by Boltzmann, and his statement that the entropy S is equal to a constant K times the natural logarithm of W. Actually, when he was doing it, he used logs because they could use a slide rule. So on his grave, it actually says K log W, where W is a number of microstates. You remember in one of the lectures, I went through all the possible arrangements of molecules, okay? Delta S is final minus initial. Oops, sorry about that. So if I have more states in the final versus the initial, I have an increase in entropy. If I have less possible states, I have a decrease in entropy. And we can see that, you know, if we take a solute and dissolve it, we're going to have an increase in entropy. Matter and energy are going to be dispersed, and we have an increase in the number of microstates. Now, the entropy of a substance increases with temperature because there's more possible ways that it can be arranged. Okay, an increase in molecular entropy, an increase in molecular complexity leads to an increase in entropy. And we can predict changes in entropy. Entropy is going to be higher for a higher temperature, a bigger volume, more complex molecules, increase in moles of a gas, a bigger sample size, larger atoms, more heavier atoms. Gas relative to liquid or solid is going to be much greater, or liquid is going to be higher than a solid. We can predict each of these, and you should be able to do so, okay? So we can take a look. Now, which of these two is going to have the higher molar entropy? This is a more complex molecule. Propane is going to have the higher one. At a bromine gas and bromine liquid, the gas is going to have the higher entropy, okay? If I take a mole of CO2 at 3 atmospheres and a mole of CO2 at 1 atmospheres, this one is going to be at a much lower volume. This is going to be as a higher volume, so this will have the greater entropy. And we could predict a reaction, 2NO plus O2 yields 2NO2. Notice I go from 3 molecules of gas to 2 molecules of gas, so we would expect to see a decrease in entropy for this particular one. On this one, we have no molecules of gas here, and we have molecules of gas here. That's going to be a great increase in entropy. And in this one, we go from 2 solutions to a precipitate. We would expect to see a decrease in entropy for that one. Okay, so spontaneous processes tend to increase the entropy, and the second law of thermodynamics is the entropy of the universe is always increasing. So if we look at our system and we compare the delta H and the delta S, we will find that something that's exothermic with a positive entropy change is always going to be spontaneous. And you can read the rest of this one. Standard molar entropies are something that we can look up in the back of the book. It all comes from Ludwig Boltzmann and his third law of thermodynamics. And that allows us to actually calculate the absolute entropies of substances. That's why when we look up in the back of the book, we don't see a delta S, we just see an S. Now these are at standard temperature. S will change slightly at different temperatures, but we're going to look at the standard molar entropy of a substance. Okay. Again, these are in the appendix in the back of your book, along with enthalpy and free energy, which we will talk about here in a moment. And we can take Q reversible over T, and we can get this. So if I want to find the delta S for boiling water, going from a liquid to a gas, I take it at the boiling point, and Q reversible is the delta H for that reaction. That's going to give me a great increase in entropy. and you can determine it through physical and chemical processes. This is the form that I've given in several lectures. Remember to take into account the coefficients when you do this. So here we have 2H2O. Don't forget to multiply by the 2. O2. So sorry, 2H2O here, multiplied by the 2 minus 2H2 and 2O2. Now, remember, for the enthalpy of formation of an element was 0. But because we can actually measure the entropy, it's not the entropy of formation, it's the actual entropy. We have values for everything, even elements in their standard state. Okay, and you can calculate entropy changes for different reactions. This is another statement of the second law of thermodynamics. A process is spontaneous if the delta S of the universe is greater than 0, but we need an easier to measure thing than that. Now, taking a look, it's exothermic. If I want to melt ice, I have to add energy to it. This is endothermic. This one, if I go from a liquid to a solid, is exothermic. And which occurs spontaneously? Okay, trick question. Okay, because at some conditions ice is going to melt, and some conditions ice is going to freeze. Okay, yeah, so we can take a look at the temperature role in there. And we can say that when the temperature is greater than 0 Celsius, we spontaneously go from a solid to a liquid. When it's less than 0, we go from a liquid to a solid. Reactions tend to be spontaneous when we have an exothermic reaction that has an increase in entropy. Or as the second law states, it's one that results in an increase of entropy of the universe. And going through a couple things here, we are going to calculate the delta S of the system. We can calculate, I don't like using this equation because the heat gained by the surroundings sometimes is hard to measure, but you need to be aware that that calculation exists. I think I even have a homework problem that has that. So we can calculate the entropy change for the universe, or for the surroundings for the reaction here. Here's our entropy change for the universe. I'm not going to go through that one. You can take a look at that. All right, what I want to talk about now is Gibbs free energy. Energy that is free predicts if something is spontaneous. Okay, and now Willard Gibbs took a look at things, and he asserted the maximum non-PV, PV is pressure volume work available to the system, must be a function of enthalpy and entropy. G equals H minus T delta S. Now this is the general form of the equation. We're actually going to look for things that we can measure, which are changes in the free energy. If you get into upper level classes, you can take a look more into thermodynamics. But for us, we're going to kind of simplify it a little bit. We're not going to look at G equals H minus T delta S. We're only going to look at a closed system. So we're going to look at delta G equals delta H minus T delta S. If there's only one equation you remember from this chapter, this is going to be it. Okay, delta G is a state function, which means it only depends on the initial and final states. And we can actually calculate it with products minus reactants using the table in the back of the book. Okay. Now, if you take a look at this, this is just some definitions here. If the reaction is exothermic, this tends to be negative. If we have an increase in entropy, this entire term with a minus here ends up being negative. So therefore, if delta G is less than 0, we have a spontaneous reaction. We can now calculate delta G to determine whether a reaction is going to be spontaneous or not. Okay, so if I have an increase in enthalpy, in other words, I have an endothermic reaction that has a decrease in entropy, it's not going to be spontaneous. It's going to be reactant favored. You can read through this one. A reaction proceeds spontaneously towards the minimum in free energy, which corresponds to equilibrium. And we can calculate this. I'm not going to go through all the derivation of this. Remember, Q is equal to the products to the power of their coefficients over the reactants to the power of their coefficients. And at equilibrium, we know delta G is 0 and Q is equal to K. So delta G naught is equal to negative RT ln K. Knowing one quantity yields the other. We're going to use this in the lab this week. And we can take a look at this table of the relationship between Q and delta G. You can read that on your own. Under reversible conditions, both the enthalpy and entropy are state functions. So Gibbs free energy is a state function, so we can write this equation. And we can look up standard molar free energies in the back of the book. Note that just like enthalpy of formation, the free energy of formation for an element in its standard state is 0. Notice diamond is not the standard state for carbon, so its free energy of formation is not 0. Okay, so you can actually go through and calculate in Appendix L of your text. If you want to stop the video and work through this, the solution is where you see there. I'm just going to go ahead and move on. We can calculate delta G. For this one, ammonium nitrate solid goes to ammonium nitrate aqueous. Do we expect this to be product favored? Well, there definitely is an increase in entropy going from a solid to this, but it's endothermic. So is it enthalpy or entropy driven? We can pay attention to what temperature it is. Okay, so if I have an exothermic reaction that has an increase in entropy, it's always going to be a negative delta G. If I have an endothermic reaction with an increase in entropy, it's going to be spontaneous at high temperatures. If I have an exothermic reaction that has a decrease in entropy, it's going to be spontaneous at low temperatures. Now that high and low is relative to the particular reaction. So we could actually calculate at what temperature delta G changes from a positive to a negative value. Here is an example. I'm just going to go ahead and go through this. You can look through this on your own. And we see that the temperature at which that changes is approximately the melting point of iron. Delta G does not predict spontaneity, or sorry, it does predict spontaneity, and you can see the summary of that here. There are two different ways to calculate delta G. If we have all the values, we can calculate it directly, or we can calculate delta H and delta S and calculate it from delta G equals delta H minus T delta S. Notice S is going to be given in joules per mole. Delta G and delta H are in kilojoules per mole, so we need to pay attention to that. If you have all but one of these, you should be able to solve for any of the other. Okay, so the free energy depends on the enthalpy term and the entropy term, and you can see whether something is going to be entropy or enthalpy dependent. Here's an example. Wine is exposed to air. The ethyl alcohol is oxidized. You can look through the reaction of that and do that on your own. Here we find the changes and we calculate delta G at different temperatures. Notice the delta H is pretty much the same. Delta G is going to be the same, so the T delta S, this term is going to be different for these. All right. Relationship of delta G naught to K. If we're at equilibrium, this is going to be 0. This value is going to be K. So delta G naught equals negative RT ln K. And you can see the relationship between delta G and K there. So we're in the summary of the chapter. Delta G is the energy or the free energy, available energy to do work. And that is the end of our slideshow for chapter 18. I will be doing another one for chapter 19.